Welcome to Calc BC, Lesson 2.1, Basic Differentiation Rules. There are 4 lessons in this unit, and this unit covers College Board units 2 through 5. So we're just going to do a big sweep of all of those units. We're not going to get into every single nitty-gritty detail like you did last year in Calc AB. So for this first lesson, we're going to cover a lot of the basic topics from the College Board's Unit 2, called Differentiation, Definition, and Basic Derivative Rules. So you can see we're going to be talking about, just the definition of a derivative, how to estimate derivatives at a point, power rule, product rule, quotient rule, some basic things like that. So I'm going to pause now and get ready for the notes. All right, so here are our notes for 2.1. We're going to start off with hopefully some pretty simple derivatives. So the first function we have is f of x equals x cubed. And you need to remember your power rule, right? So you bring the 3 and you multiply it by the coefficient, which in this case was just a 1. So we bring a 3 in front and we take the exponent and we subtract 1. And that's our derivative, right? And this mark right here means f prime of x. That's our notation for derivatives. Hopefully you remember that. Another way of writing a derivative might be y prime instead of y. And root x, I like to think of that as x to the 1/2. And then we just follow the same rule that we did for the first one. So now we bring the 1/2 in front and it becomes x to the negative 1/2. You can just leave it like that. If you wanted to get fancy, a negative exponent means this moves to the bottom and it's a 1/2 power. So it's really like 1/2 root x. Let me pause this for just a second. All right, sorry for that interruption. Here we go. So it's 1/2 root x is another way of writing that because the x can move down with the 2 and the negative 1/2 power becomes a root x like that. All right, if we look at letter C, 1/t to the 4th can also be written as t to the negative 4th. So when that's kept in mind, just like before, we can bring the negative 4 in front. We subtract 1 from the exponent, it becomes negative 5. If we wanted to write this with no negative exponents, it could be negative 4 over t to the positive 5th. The 4 stays on top, it doesn't have a negative exponent. The t does have a negative exponent, so it moves to the bottom, and the exponent becomes positive. All right, so that's the answer to that one. Letter D, f of x equals 5. Anytime you just have a constant, think about what that graph looks like. It looks like a horizontal line straight across. What's the slope of that line? The slope is 0, and the derivative of a constant is 0. And letter E, this is another notation for a derivative, d over dx of this. 5x cubed would be 3 times 5, so 15 x to the, and you take the 3 and you subtract 1, so it's x squared. All right. So there's some power rule for you as well as some different notations for derivative. Hopefully that makes sense. Let's keep going here. We got 2 more examples like this. For this one, now we have multiple terms, right? So all we do is we take the derivative of each term separately. So 4 times 3 is 12x squared minus 10x plus 7. Whenever you have an x term, right, it's like the exponent is 1. And when we subtract 1, we get 0. X to the 0 power is 1. So the x goes away. We're just left with the 7. And the 3 is completely gone because the derivative of a constant is 0, like we saw up in letter D. And in the next one, I think it's going to be easiest. Instead of trying to use a quotient rule, if we just divide each term by x for this one. So we can do 5x to the 5th divided by x is 5x to the 4th minus 3x to the 3rd plus 4x to the negative 1. All right, and we're going to take the derivative now of each of these terms, and we get 20x to the 3rd minus 9x squared. Negative 1 times 4 is negative 4x to the negative 2. And if you wanted to rewrite that, you could write 20x cubed minus 9x squared minus 4 over x to the positive 2. Either of those answers is fine. It doesn't say that we have to have any sort of specific simplified answer here, so that would be fine. Let's keep going. Next example, determine the points at which the given function has a horizontal tangent line. So horizontal tangent line. First of all, let's think about what that means. Horizontal, we know, is straight across like this. And if that's our tangent line, then it must be because of a maximum, or if it was above, it would be a minimum value, right? As long as this function is continuous. So in order to figure this out though, it's going to be easiest if we just find the derivative. And then set the derivative equal to 0, right? Because if there's a horizontal tangent, it means that the slope at that point is 0. So if we take the derivative, we're going to get 3x squared minus 12. And we're going to set that derivative equal to 0. Because that's going to give us any time where the derivative is 0, any time where the original function had its horizontal tangent line, because it has a slope of 0 at the point. And so we have to solve this for x. There's only one x term, so we can actually just add the 12 to the other side instead of factoring. Then we can divide by 3, and we get x equals plus or minus 2. Don't forget that plus or minus there. Whenever you initiate a square root, you have to include a plus or minus. Don't forget that. So now we go back to the original function. It wants to know the points where we have a horizontal tangent line, not just the x value. So we're going to have to find f of 2. And f of negative 2. We end up with negative 16 and 16. So our 2 points are 2 comma negative 16 and negative 2 comma 16. And if you take a look at the graph of this curve, you will notice that those are the two maxes and mins, and they do have a horizontal tangent line. There you go, okay? All right, let's keep going. The next example, we have f of x equals x cubed minus 3x squared plus 4. Find the average rate of change. Okay, so rate of change is another way of saying slope. And to find the average rate of change, we use this formula, which looks a lot like the slope formula, right? It's f of b minus f of a over b minus a. And our a is going to be 1, and our b is going to be 5. So if we find the slope between 2 points on a continuous curve, the slope of the line that connects those 2 points is the same as the average slope between those points. That's one of the properties that you learn in differentiation. So let's plug this in here. So we have f of 5 minus f of 1 over 5 minus 1. And just to be clear, take a look at this curve here. This is a regular old polynomial. There's no reason that this would be discontinuous or undifferentiable at any point. So that definitely is going to work when we plug this in here. Okay, so f of 5, so I'm plugging 5 in for x. And then I'm plugging 1 in for x for the second part. And on the bottom, I have 5 minus 1, so it's going to be 4. So we end up with 5 cubed minus 3 times 5 squared plus 4, which is 54. And then 1 cubed minus 3 plus 4 is 2. So we end up with 52 divided by 4, which is 13. So that's the average slope from 1 to 5 on this curve, okay? Letter B, find the instantaneous rate of change of f at x equals 3. All right, so what we're going to do for this part is to find an instantaneous rate of change instead of the average, we actually take the derivative. So I'm going to take the derivative using our derivative rules. So we get 3x squared minus 6x plus 0, because the 4 goes away. And we're going to plug in an x value of 3 and see what we get. So we end up with 27 minus 18, or 9. Okay, So there's a difference between average rate of change and instantaneous rate of change. Hopefully that makes sense. And I'm going to keep going. Sketch the graph of a function f such that the first derivative is less than 0 for all x and the rate of change of the function is increasing. So this first part here tells you that the slope of the original function is negative. And if the rate of change is increasing, so the slope is increasing, that tells us that we are concave up. In other words, we're going to have a curve that looks more like a smile than a frown, right? We're concave up, and but we need to always have a slope that's negative. So this is just going to be a rough sketch, and there's lots of different graphs that this could look like, but I think the easiest one is to think about, okay, so we have to be going down always, but we also have to be concave up. So it's going to look something like this. The easiest way to do that is to think of it as having a horizontal asymptote, because then it is still always concave up, but the slope's still also always negative. Hopefully that makes sense. We'll have loads more chances this year to look at graphs for concavity and slope, etc. But let's keep going. Next example, find a and b so that f is differentiable everywhere. All right. So if a function is differentiable, two things have to be true. One, the function has to be continuous, and two, it has to be differentiable. So the first derivative also has to be exist everywhere. So the first original function has to be a continuous curve with no points or no holes or anywhere that would mean that the first derivative doesn't exist at a point. In other words, what we're going to have to do here is, well, I'll take you step by step through it. So the first thing we're going to do is think about that this is a piecewise function. This top part is true for x is less than or equal to 2, and the bottom part is true for x is greater than 2. You can already tell that this part is a line and this part is a curve. So somehow when these two meet, they have to meet at the same point, and they also have to meet with a smooth curve and not a corner. So we're going to have to figure out how do we make sure that their function value and their first derivative are the same. So the first thing I'm going to do is think about that when x equals 2, the left side, so in other words, the ax squared plus 1 is going to have to equal the bx minus 3. Now that doesn't always have to be true, but it does when x equals 2, because that's where these two meet. In order for it to be differentiable, it has to be continuous. So these have to meet at the same y value. So I'm going to plug in 2 for x. So we end up with 4a plus 1 equals 2b minus 3. If I solved this for a, I would get 4a equals 2b. I'm just going to subtract 1 and then divide by 4. So we get a equals 1/2 b minus 1. Okay, so we're going to think of this almost like a system of equations here, because now we're stuck. We only have one equation so far, so we can't find a and b. So let's kind of go back to our original and think about the first derivatives also have to be the same at 2 in order for this to be differentiable at 2. So if I take the derivatives, and I'm going to think of a and b as being constants, not variables. So if I think of that up here, the x is the variable. So if I do the power rule, it's going to be 2 times a x to the first. So it's going to be 2ax to the 1. The 1 is going to go away. That has to equal bx minus 3. So 1 times b is b. The x goes away, and the minus 3 goes away. So 2ax has to equal b, again, when x equals 2. So now I'm going to plug in 2 for x. So we get 4a equals b. Okay, so now we have a equals 1/2 b minus 1, and 4a equals b. So I'm going to plug this in for a over here, flash back to algebra 2. And we're going to solve for b. This is called the substitution method. 4 times 1/2 is 2. 4 times 1 is 4. Subtract b, and we get b minus 4 equals 0. So b equals 4. And then over here, I'm going to plug in 4 for b to see what I get for a. So a equals 2 minus 1. So a is 1. So we got an a and a b so that the function was continuous and differentiable. All right. A little bit of a trickier question there. Let's keep going. At time t equals 0, a diver jumps from a diving board that is 32 feet above the water with an initial velocity of 16 feet per second. Use the position function where the v naught, that's what we call it when there's a sub-zero, you say v naught, it's like a physics term right there, is initial velocity, and s naught is the initial position. A, when does the diver hit the water? And then B, find the instantaneous velocity when t equals 1 second. Okay, so when does the diver hit the water? So let's think. The position function is given. So I'm going to write that down. And we are already told that the diver jumps from a diving board that is 32 feet above the water and has an initial velocity of 16 feet per second. So I'm going to plug that in. So we have a v naught initial velocity of 16 and an s naught, an initial position of 32. And we want to know, when does the diver hit the water? So when he hits the water, the position, which is this function, should be 0, right? Because he's going to be, instead of being elevated, he's going to be back to sea level, which is a vertical position of 0. So we have 0 equals negative 16t squared minus 16t plus 32. And we're going to try to solve this for t. So I think the easiest thing to do here to factor this quadratic is to think, I can pull out or divide each of these by 16, so I should. Also, personally, I learned that when I factor quadratics, I don't want the first term to be negative. So I'm going to divide everything by negative 16. And we get 0 equals t squared. What am I doing? This was supposed to be plus, wasn't it? Why did I put it as a minus? Yeah, you're probably already getting mad at me because I did that. But yeah, that should be a plus the whole time. So now we're divided by negative 16, and now it becomes negative. So now we have negative t here. And then 32 divided by negative 16 is going to be negative 2. Okay, so then we're going to factor. It becomes t minus 2 and t plus 1. So our times are 2 and negative 1. And again, that's in seconds. And so we are at the water at negative 1 second and at 2 seconds. Negative 1 doesn't really make sense. That's before we even started. If we think about what this graph looks like, it's something like this. And this is where the diving board is. So the time only starts this way. This part is an irrelevant part of the graph. We jump and then arch and then end up in the water at this time. So I'm going to cross off that negative 1. That's irrelevant here. And it's, when does the diver hit the water? 2 seconds after the jump. That's what that means. B, find the instantaneous velocity when t equals 1 second. Okay, so Let's see. To find the instantaneous velocity, since we have a position function, we can take the first derivative. So it's going to be negative 16 times 2 is negative 32t plus, and if we think about what we already plugged in, because we're looking at the same scenario here, 16t, the derivative is going to be 16. And then the 32 goes away. We are thinking about 1 second, so we're going to plug 1 in for t. And negative 32 plus 16 is going to be negative 16, and that's in feet per second. So that's our instantaneous velocity at 1 second. Since it's negative, it's going back towards the water. It's not going up anymore, it's going down. But that makes sense to us. Okay, so that's our instantaneous velocity. And we're going to move on. Next question. The graph of a position function is shown. Sketch the velocity function on 0 to 9. So what we're doing here is just thinking about what is the first derivative graph going to look like. In other words, we need to know what the slope is. And lucky for us, we have pretty straight lines here. So let's figure out from 0 to 4 along the x-axis. What is the slope of this line? And it is up 3 over 2, up 3 over 2. So positive 3/2. So from 0 to 4, we're going to have a straight line across at 3/2. Because that's our constant slope the entire time, right? Then from 4 to 7, it's a straight line, so the slope is 0. A horizontal line, so the slope is 0. And then from 7 to 9, 1, 2, 3, 4, 5, 6, yeah, 7 to 9, it's up 1 over 2, so the slope is a half. And that's our velocity function. That's all it was asking us to do there. Let's keep going. Y equals x cubed times cosine x minus 2 times sine x. Find y prime. Okay, so let's think about this. We've got a lot going into this one question, right? Because this is introducing us to the product rule. The product rule, which says that if f of x equals u times v, then f prime of x equals u times v prime plus v times u prime. We also have our trig functions, right? And so there's a kind of a pattern that goes into the derivatives of sine and cosine. So I'm going to write that over here. If our initial function is sine, the first derivative is cosine. The second derivative is negative sine. And the third derivative is negative cosine. And then it goes back and cycles back to sine. And so the way that I've learned over the years to remember this is to think about the first letters here. And we have Santa Claus, negative Santa Claus. Or Santa Claus, negative Santa, negative Claus. And then it goes back. Okay, kind of silly because it's not that hard to remember in the first place. But, you know, it is what it is. That's how I remember it. And it always cycles back. Now, when we do integrals, we'll have to remember that this goes backwards, but we're not going to think about that yet. All right, so we've got the power rule, and we've got Santa Claus, negative Santa, negative Claus. So we're going to use that to break down this first term here in this equation that we're trying to factor slash find the derivative of, not factor. So if we take a look at this, what I'm going to do is, since this is a product, I'm going to label that u is the x cubed, and the v is the cosine x. And so then u prime is the derivative of 3x squared, the derivative of x cubed, which is 3x squared. And v prime is going to be the derivative of cosine. So if I look over here, one level down from cosine is negative sine x. And then we're going to do the product rule. So now we can write that y prime equals, so it's u times v prime plus v times u prime. Okay, so that's the first two terms. And if you switch u and v, you'll get the same answer, but the terms will just be switched around. And then we have to take the derivative of this second term up here, minus 2 sine x. And the derivative of sine is going to be cosine, so it's going to be minus 2 cosine x. So anytime that there's a constant in front of the trig function, it just stays there. Okay, and then we just kind of multiply these together. So we have negative x cubed sine x plus 3x squared cosine x minus 2 cosine x. I don't have any like terms, so we're stuck with that. Next question, sine x over x cubed. We have a quotient, so we're going to use the quotient rule, which is if the original is u over v, our quotient rule is low d high minus high d low all over the square of what's below, right? Maybe you remember that. So it's low, derivative of the high, minus high times the derivative of the low, all over the square of what's below. Perfect, okay. So let's apply that in this question. So we know u is sine x, u prime is going to be cosine x, v is x cubed, v prime is going to be 3x squared. And now we calculate this. So we have v times u prime minus u times v prime all over v squared. So it's x cubed squared. And so we have what? X cubed cosine x can't be multiplied further than that. Neither can the second part. And this is all over x to the 6th, because x cubed squared is x to the 6th. Now we have an x cubed, an x squared, and an x to the 6th in every term, so we can pull x squared out of every term since we have a fraction here. So we are left with x cosine x minus 3 sine x over x to the 4th. And that's our derivative. All right, next question. F of x equals x squared plus 2 over the 4th root of x. Now, we could go through the whole quotient rule for this question, but this is a trick question in disguise, because if I rewrite that denominator, it's now x to the 1/4, and that can actually be distributed to each term in the numerator. We can have x squared over x to the 1/4 plus 2 over x to the 1/4, which can be rewritten as 2 minus a 4th is going to be x to the 7/4. Good old exponent rules. You need to make sure you remember that. And for the right fraction, we have 2x to the negative 1/4. All right, and so now for the derivative, all we have to do is use our normal derivative rules instead of thinking about the quotient rule. So we can use our power rule. So we have 7/4 x to the 7/4 minus 1, which is 3/4. 2 times negative a 4th is going to be negative 1/2. X to the negative 1/4 minus 1, which is negative 5/4. There we go. Next question. If you have a quotient in which the numerator is a constant, it's easier to write it as a function with a negative exponent and use the power rule. So that's similar to what we just did. So we can write this as 9/5 x to the negative 2. And now we can just use the power rule. So 9/5 times negative 2 is going to be negative 18/5. and we have x to the negative 3. And you can just leave it like that, or you can move the x to the third to the denominator if you want. All right, hopefully that's not too bad. Let's take a look at the next and final page of the notes. We can use the quotient rule to derive a rule for the derivative of other trig functions. So we've already talked about sine and cosine, right? Santa Claus, negative Santa, negative Claus. Now we're going to talk about some of the other trig functions. So let's take a look at finding the derivative of tangent. So something that hopefully you remember is that tangent can also be written as sine over cosine. That's something that we learned back in pre-calc. And this is a quotient, right? So let's use our quotient rule, low d high minus high d low, all over the square of what's below, and see if we can simplify that to something that makes sense, right? Maybe you already remember what the derivative of tangent is, but we'll get there. So let's write this out. So we have low derivative of sine is cosine minus sine times the derivative of cosine, which is negative sine, all over the square of cosine. And remember, when you have a trig function that's squared, it's standard to write the exponent before the x. That's the general notation which shows that the trig function is squared. And to simplify this, we end up with cosine squared x plus sine squared x all over cosine squared x. And if you remember back in pre-calc, sine squared x plus cosine squared x is 1. So this really just equals 1 over cosine squared x. And 1 over cosine is secant. So this is secant squared x. Okay, so that's how we can determine the derivative of tangent. Now we don't have to do those steps every time because we're just going to memorize that that's the derivative of tangent. And we'll talk about that in a minute. But let's keep going. So secant can also be written as 1 over cosine. So we're going to do the same thing, do the quotient rule here and see what happens. So we have low d high, and the derivative of 1 is just 0, so that's kind of nice, minus high d low, negative sign again, all over the square of what's below. And cosine x times 0 is going to be 0. Negative 1 times negative sign is going to be sine. So we have sine over cosine squared. And I'm just going to manipulate that to make it the answer into what we are going to be memorizing here. And we can think of this as 1 over cosine times sine over cosine. And 1 over cosine is secant, and sine over cosine is tangent. Okay, so definitely write down these key derivatives that we need to know. The derivative of tangent is secant squared. And the derivative of secant is secant x tangent x. Okay, so before we talk about cotangent and cosecant, I want to tell you a little bit of a story. I went to a Calc BC teacher training 2 summers ago, and the presenter, I don't even remember her name. Geez, I used to know this. I'll try to figure that out. But she shared that one time she was shopping in a grocery store and putting items into her cart, and she goes up to the register to check out, and the line was really long, so she was just stuck in line, and she was looking over at the magazines on the shelf, and one of the magazines had PSST, psst, written on it, like encouraging people to look, right? It said psst. And her mind, for some reason, automatically thought, oh my gosh, if I just cover up the P, this is a perfect way to remember the derivatives of tangent and secant, because it's just about which way you process this. The derivative of secant is secant times tangent. The derivative of tangent is secant times secant, right? Secant squared. So if you can remember psst, then you can remember the derivatives of tangent and secant. Secant is secant tangent. Tangent is secant squared. And unfortunately, there's not something as nice as that for cotangent and cosecant. The derivative of cotangent is negative cosecant squared, and the derivative of cosecant is negative cosecant x times cotangent x. And the way that you can remember this is, instead of remembering pst, you can just remember kat. And it sounds ridiculous, but it actually works. That's what I think of in my head when I'm doing the derivatives of cotangent and cosecant. The only thing is to remember that these are always negative. The derivative of cosecant is negative cosecant times cotangent. The derivative of cotangent is negative cosecant squared. So you remember pst, and you remember kat, and you remember Santa Claus and negative Claus, and you're good to go. You cut all your trig functions and their derivatives. I want to hear all of your thoughts on that next time that we're in person. Let's keep going. So if f of x equals 3x squared times tangent x, we're looking for the derivative. We've got a product here. So we're going to use the product rule. So I'm going to start with 3x squared times the derivative of tangent, which is secant squared x, plus the second tangent x times the derivative of the first, which is going to be 6x. And I can already tell right now that that's not going to be able to simplify more than that, so I'm just going to leave it like that. There you go. There's your derivative. Next question, and the last question for this notes. Sometimes we are given the values of a function and its derivative to help us evaluate a product or a quotient. So instead of actually having the function, all we have is certain values, and we're supposed to find f prime of 2. So let's think this through here. We're given f of x. Before we even think about plugging in 2, let's just find f prime. And it's a product, so we're going to use the product. So it's product rule. So it's going to be g of x times h prime of x plus h of x times g prime of x. And we can't simplify more than that, so now we're going to try to plug in 2. Okay, and let's see what we can do with all this given information up here. G of 2 is 3, h prime of 2 is 5, h of 2 is -1, g prime of 2 is -4. So we have 15 plus 4, or 19. Okay, so hopefully you got that. Hopefully this makes sense. Thank you for watching, and I'll see you next time.